Hello everyone, welcome to the next lecture. So we are talking about diodes. In today's lecture, we're gonna see how we can use different techniques to solve the diode circuit. How we can use the basic Kirchhoff's law and or exponential model of the IV characteristics that we discussed. How we can use that, how that will come into play while solving the diode circuits. We will also talk about the different models, and we talked about a couple of models already, the exponential model of a diode and a ideal model of a diode. So we will also talk about that in terms of solving the diode circuits. All right, so we are mostly going to talk about analysis of diode circuits. So let me make a very simple circuit here. Right, so suppose that this is the input supply VDD, this is a resistance, and we have a current ID, and here is a potential drop VD. And consider we are talking about operating the diode in a forward biased condition. So this means that at least my VDD should be greater than 0.5 volts. If you remember that 0.5 volt was the current volt at which the diode will start to connect, and then we had a threshold voltage at which it is fully conducting, and that is the voltage that kind of appears across the diode. Okay, so for example, what we want to do in the circuit is we want to find the potential drop across the diode and the current flowing through the circuit, right? So we want to find VD and ID. So in terms of the forward biasing, for example, so we are currently making this assumption that we're gonna see how to solve these circuits in a forward bias condition. So if that is true, then the equation for my forward biasing is the current that is gonna flow through the diode is IS e raised to power VD over VT. So this is the exponential equation that we saw in one of the earlier lectures, right? So this is coming diode equation, and this is exponential. You can see this exponential relationship here. Another equation that we can potentially write by looking at the circuit is simply ID equals VDD minus VD over R. Now this is coming from simple Kirchhoff's law. Right, okay. So let's talk about now, so we have these two equations, and we can potentially solve this circuit either using this equation or this equation. So which of the equations to use? We can solve this, we can find the solutions or find VD and ID using a couple of methods. We're going to talk about a couple of methods. For example, find solution. So if we have to solve this, we can use a graphical method, and we can use an iterative method, iterative numerical method. So we're going to discuss both of these methods in this lecture today. All right. Let's call this equation 1 and this as an equation 2. Okay, so let's start with the graphical method, or graphical. Okay, so first let me do the graphical analysis of this diode circuit, and that will use the exponential method of the diode. Exponential. All right, so essentially that is gonna use that exponential diode equation. So what this graphical analysis requires is, what essentially we do is we plot both equations. So these are the two equations we have, 1 and 2. We are going to plot both of these equations on the IV plane, on IV graph. Right, okay, so we already know, interestingly, if you guys remember now, this is a current, this is a drop, And we saw that the diode, the actual plot of the diode is, so I am plotting this. This is how it looks like at a potential, and this is going to start to ramp up. So this is how the exponential model of the diode in the forward bias condition looks like. So since we are only talking about the forward bias, so I'm only interested when VD is greater than 0 volts. Okay, so this is the diode characteristic line. Okay, so this is good. We already know that this is coming from equation number 1. Now let's do our equation number 1, if you remember, was ID IS E VDT over VD. ID equals IS e raised to power VD over VT. And then that was a 1 equation. The second equation was VDD minus VD over R. So let's plot the second equation. So I can find the intersection points. For example, let's solve this equation for when VD equals to 0. When VD equals to 0, ID will be equals to VDD over R. And now let's solve it again. When ID equals to 0, VD will become equals to VDD. Okay, so here we have when ID equals to 0, let us suppose this is the value of VDD. This is when our current equals to 0, and when our voltage will be equals to 0, the value will be equals to VDD over R. So this is how we can find these intercept points. And now what I can do is I can just connect these 2 points. It should be so for looking at the equation, you can see that it's a linearly decreasing line. So if we can find these 2 points, if we can label these 2 points, we can just connect these 2 points together. Now this line is normally called as a load line. We're going to discuss more about the load lines in subsequent lectures as well. Looking at this equation, if you look at this equation, you can see that the slope of this line equals minus 1 over R. And also another important thing, this point of intersection here in between the load line and the diode characteristic line can be labeled as Q, and this is the operating point, we usually like to call it. And if I will do this intersection, I can find, let's say this is the voltage across the diode, this is the potential drop across the diode, and this is the value of ID. Okay. Right. So in order to solve, sorry, in order to solve the diode circuits using a graphical method, we do two things. One, we plot both of these equations, this exponential equations and this linear equation. We plot both of these equations on an IV graph, and then we find the point of intersection. That point of intersection will give us the value of ID and VD that we are looking for, right? So we draw the lines and find point of intersection, right? And that point of intersection, ID and VD, is what we are looking for here. So this is what we want to find. This is how we can find it. Of course, when you are plotting it, and if you know the values of the VDD, and then you can easily able to calculate the exact values of ID and VD. Now we are going to talk about another method, iterative method, that is more commonly used because it's kind of a numerical method, and does not involve making graphs. Okay, so let's talk about the second method, iterative analysis now. So we have method B is more like a numerical iterative analysis. Right, so let me draw the circuit again. VDD, resistance, current flowing through the diode, and a potential drop across the diode. And what we want to find is, again, we are interested in finding VD and the value of ID. Now let us suppose, while doing this iterative analysis, we also know the value of VDD that is given. Suppose that it is 5 volts, and the value of the resistance is also given, that is 1 kilo ohms. Further assume that diode has a voltage drop of 0.7 volts. This means that VD equals 0.7 volts when diode current is 1 milliamperes. So this is an assumption that we are going to make. We are going to say that, okay, diode is going to have a voltage drop of 0.7 volts when the diode current will be, and the diode current is going to be 1 milliamperes. All right, now let's try to solve this. Just by this, we can see that we have the first data point that is available, where VD is 0.7 volts and ID is 1 milliamperes. But we are interested in finding out the exact value of the VD and ID under these conditions when VDD is 5 volts and the resistance is 1 kilo ohms. Okay. So let's let's start the solution, and I'm going to call and since this is an iterative analysis, so I'm going to call the first step as a first iteration here. Okay, and you're going to realize when we are going to do the second iteration, you will realize that now we are kind of repeating the analysis again. So now I am going to start with the first iteration. In the first iteration, we will directly start with the Lecture6 laws equation. ID equals VDD minus VD over RD over R here, sorry. So VDD is 5 volt. VD, I know the VD. I'm going to use this data point, 0.7 divided by R, 1 kilo ohms. This is going to come out to be 4.3 milliamperes. Right, so my initial data point was the potential drop across the diode was 0.7 and the diode current was 1 milliamperes. Now I got another diode current, which was 4.3 milliamperes. Okay, so this is interesting. Now what we can do is we need to find a new value of the VD as well, right? So essentially, we need to find a better estimate for VD. Okay, now from one of the previous lectures, if you remember, we studied this equation. V2 minus V1 is 2.3 thermal voltage log of 10 I2 over I1. And so let me simplify this as so 2.3 times VT is 25 millivolts. 2.3 VT is 60 millivolts. Okay, I'm going to plug this over there in the equation here. So the V2 now will be equals to V1 plus 60.06 volts log of I2 over I1. Now interestingly, you can see that so I'm interested in finding V2 when my I2 is my new current value 4.3 milliamperes, and my V1 will be 0.7 volts and I1 will be 1 milliamperes that I started with. So I know the three values, and I can easily calculate the value of V2 using this equation. So if I will plug in the numbers now here, so V2 equals V1, which is 0.7 volts plus 0.06 log of I2, 4.3 over 1. The value of the V2 that we will get will be 0.738 volts. Now you can realize that we are kind of converging on the values of VD and ID. So the new values that I've got for the VD is, so the VD now, the new VD is 0.738 volts, and the new ID is 4.3 milliamperes. Okay. Now what we do is, now we are going to do a second iteration, and we will see that how far apart the VD and the ID will come from these values. And then if they are far apart, then we have to do a third iteration, and then the fourth iteration. If the values come to be very closer, then we can stop the process there. All right, we are going to perform in the second iteration, we're going to repeat the exactly same procedure. Now we are going to start with these two numbers. So this means that I'm going to start with the value of the VD, 0.738. I'm going to plug it here, and then I'm going to repeat the entire procedure. Okay, so let's do the second iteration and see what numbers shall we get. Okay, in the second iteration, again, I'm starting with VDD minus VD over RD. VDD is 5 volt. This is 0.738, the new value of VD, divided by RD, the new value of the current that I will get is 4.262 milliamperes. So this is the new value of the current. Sorry. Now I already know that. Now I have to find the new value of the VD. So V2 equals V1 plus 0.06 log of I2 over I1. Now I'm going to plug in the values here. Now I know that my V1 was from, and this is coming from the results of the first iteration, 0.738 volts. I1 was 4.3 milliamperes. I'm interested in finding V2 when my I2 is a new value, 4.262 milliamperes. Okay, so let's plug in the numbers here. V2 is V1, 0.738 plus 0.06 log of I2, 4.262 over 4.3. So if you will plug all the numbers, the new value that you will get, it will be very close. Essentially, it's like almost similar. So you're gonna get the same value if you round it off, the value of the V2. So this is the new VD that we get, 0.738 volts. And the new ID, so this value that we got is for this current. So the new value of ID is 4.262 milliamperes. Now if I will compare these two values with the earlier values that we got from the first iteration, they are very close. The VD is almost exactly the same, and the value of the ID, 4.3 and 2.62, the values are also very reasonably very closer to each other. Right, so since second iteration values are very close to first iteration, we can stop our analysis, iterative analysis here. Analysis here. and we can say that our solution, our final values of ID is 4.262 milliamperes, and the final value of VD is 0.738 volts. Okay, so this is how we can do this iterative analysis, in which we can start with we can start with the values that are given in the questions. We perform the first iteration, using this Kirchhoff's laws equation, and then using this equation. So this is another important equation to remember, in which we can find the difference in the voltages. If we know the value of the current and the voltage, then we can find the other values of the current and the voltage. And this is specifically for the PN junction. So we're gonna potentially use this thing, use this equation as well in our transistors chapters as well, in some of the problems. So anyways, the take-home message from this example problem is that You want to make sure that you will continue your iterative analysis till the values comes very close to each other, and when they are reasonably close, then you can stop this analysis. Okay, there's one more thing that is left in this lecture, and that is kind of giving you a final summary of all the models now. Sorry. Models of the diode. So here is the overall summary of all the models of the diodes that we have discussed. We have discussed 2 models by now, and I'm going to show you a third model today. One is an exponential model, and the other is an ideal diode model. So let's talk about, let me write those models again. Exponential model, we know the equation for the exponential model. Here's a V, here's a I, and we know that we already saw that, right? So this was a model equation, right? Exponential model for p-n junction. So our equation, our current equals to Is e raised to power V over nVt, and we have normally assumed n equals to 1 minus 1, right? So this is the equation for the exponential model. Right, so important thing about this model is that it's the most accurate device model for diode operation, right? Accurate device model for diode operation. However, it requires solving nonlinear equations, right? So if you're going to employ this model, you have to solve this nonlinear equation, and we kind of did that in our iterative analysis. For example, like in iterative analysis. All right, the second model is our ideal diode model. So let's make the VI characteristics for that as well. V and I. Our ideal diode model is, this is a reverse bias, it is open circuit, and at 0 it will become short circuit. So this is an ideal diode model. And in that case, we discuss this in detail, right? So when the current equals to 0, when voltage is less than 0, right? And our circuit behaves as an open circuit, and current will become greater than 0 when voltage will become 0. So this will become a short circuit. All right, so this is our ideal diode model. We discussed that in detail previously. Now I'm going to introduce a third type of a model, which we normally use as well, and it is called as a constant voltage drop model. The constant voltage drop model so essentially what we do is, if I can plot the IV characteristics of this model as well. So this is V and this is I. So essentially, rather than using this exponential, rather than using this exponential equation, exponential curve, we still use a step function at a particular voltage value. So we say that at 0.7 volts or at a specific threshold value, it will start to conduct. So essentially, so what is happening in the terms of the circuit, that if I have an ideal diode, assuming this to be an ideal diode, essentially what I'm going to have is, assuming this to be ideal diode, what I'm going to have is a 0.7 volt battery attached to the diode, right? Essentially, this is that barrier voltage that is present in the p-n junction. And so another good thing about this is this model is a good approximation since forward conducting diode has a voltage drop around, and we discussed that, in between 0.6 to 0.8, and we can normally assume it to be 0.7 volts, right? So we discussed this thing in detail that for a real diode, there is a potential drop across the diode lies anywhere in between 0.6 to 0.8 volts. Normally we can assume it to be a constant 0.7 volts. So this is a voltage drop model in which we can assume there is a potential drop of an exact 0.7 volts across the diode, or whatever is specified in the question, or if you're using a silicon diode or some other diode. Okay, so these are the three models, and going back to the circuit now, I wanna show you the differences, what sort of the differences that we get in the answers if we are solving the diode circuits with any of these models. Right, so for example, again I'm gonna draw the same circuit that we have been doing in this lecture. VDD, R, ID, plus minus VD. And we know that VDD is 5 volt and R is 1 kilo ohms, and we were interested in finding VD and ID, right? So let's solve the circuit again with all the three models. We already solved it for exponential model. With the exponential model, the answers that we got was VD was 0.738 volts, and ID was, what was ID? 4.262 milliamperes. Exponential model, we solved that using iterative analysis. All right, now let's solve this thing using an ideal diode model. Now I'm going to solve the circuit again using ideal diode model. Ideal diode model assumes, it does not assume any potential drop across the diode in the forward conduction. And since we have a VDD which is 5 volts, so it is in the forward bias condition. So this means that the potential drop across the diode VD is going to be 0, right? And the ID will simply be VDD over R. Over here it will be 5 volts over 1K, 5 milliamperes. All right, now let's solve this using constant voltage drop model. Constant voltage drop model shows that the potential drop across the diode is going to be 0.7 volts, and the current across it will be VDD minus VD over R. So 5 minus 0.7 over 1K, 4.3 milliamperes. Now look at all the values. For the exponential model, this is the ID and the VD values we got. For the ideal diode model, so these are the values we got. And for the constant voltage drop model, these are the values we got. If we look at the values, right, for an ideal diode model, of course it is slightly off, because it's we are assuming it to be an ideal diode, and we are not talking about the barrier voltage or the real operation of the PN junction. However, when we consider the real operation of the PN junction, we realize that the exponential model and the constant voltage drop model works pretty close to each other. Right, over here your current differences are 4.262 versus 4.3 milliamperes, and the voltage drop across the diode is rather 0.738. It is 0.7 in terms of a constant voltage drop model, right? So these models works pretty reasonable. Okay, So this is all what I want to talk about in today's lecture. Right, so in today's lecture we talked about how we can solve the diode circuits using a graphical analysis method and using a numerical iterative analysis. Most of the time we use numerical iterative analysis, is most commonly used. We also discussed the different models of the diode, the exponential model, the ideal diode, and constant voltage drop model. And we kind of compared their values. If we are going to use any of these models and solve a diode circuit, what differences in the values can we expect? We expect very close values in terms of a constant voltage drop model and an exponential model. Okay, so with that, this finishes up our lecture today, and I will talk with you in the next lecture. All right, thank you so much. Bye bye.